Now, as we have discussed before, that EMF of a cell is electromotive force, which is actually not a force. It is the maximum terminal voltage across its terminals. That is, suppose this is a cell of EMF E. For example, I'll be taking it, let's say this is 1.5 volts. Okay. Now, when this cell is connected across an external resistor, the resistor will get only 1.4 volt or even less than that. So where is this 0.1 volt going up? The 0.1 volt is consumed within the cell by internal resistance of the cell. So that is why we don't say that, or we don't write the configuration of cell like this. We always write it like this. If we have to denote cell of EMF E, then there will always be an internal resistor mentioned across it, because some part of its voltage is going to get consumed by the internal resistance. So this is what the circuit diagram looks like. We have an external resistance R, which is connected across a cell of EMF E and internal resistance small r. Okay. So let's say I amount of current is flowing in this circuit. So the equivalent circuit, I can read out this circuit like this. I have drawn the external resistance, EMF and the internal resistance. You can draw this internal resistance R anywhere, on this side or this side, that hardly matters. This is just a show that the internal resistance is present in the cell. So now the same circuit I, R, okay. Now this whole E is consumed where? First of all by this, which is I into R, and then by this, which is I into small r. What is this term? I into R. This is the terminal voltage or potential difference which is received by this external resistance, because we don't have actually this, we have only this circuit. So this is the current into I into R. This part is the potential difference of this cell. So this E is equal to V plus IR. This is the main formula from which you can derive anything. You can find the value of small r, you can find the value of capital R. See, in some books what they have done, I'll write it here itself. E is equal to V plus I into R. I am dividing the whole equation by V. I'll get this. This is what? E upon V is equal to 1 plus I upon V is how? V upon I is capital R. So I am taking this I on the denominator of V. That is why I am getting V upon I as R. So in some books they have written this formula, in some books they have written this formula. Now, as we have just discussed the EMF of a cell, let's do some combinations of cells. How can cell be connected across a circuit? Cells can be represented or connected in a circuit in series or in parallel. So consider any simple circuit which you have definitely seen, like in remote control cars or in TV remotes, anywhere where you are using two 1.5 volt batteries. What do? You connect them in series or in parallel. You always connect them in parallel because you get the net voltage to be 3 volts, because each is of configuration 1.5 volt, right? See, so I'll be writing, now we are doing cells combination, okay? Combination of cells. First of all, if I connect a 1.5 volt cell with another 1.5 volt cell, what are they becoming? They are becoming total 3 volt. And suppose this is 1.5, this is 1.5, and I am connecting another cell in opposite order, it will be minus 1.5, because this is potential difference in reverse order. So the effective would be only 1.5. Getting my point? So when cells are connected in series, it is made sure that the cells are in the same order. Okay. Now suppose there are n cells which are connected in series across an external resistance of R. Okay. So each configuration is EMF E and internal resistance R. Now I want to find the total current of the circuit. What is the total current? Total current is simply total voltage across the circuit, or total voltage across this R divided by total resistance. This would be the total current or total potential difference. This is E plus E plus E. There are total how many cells? n cells. Okay, so the total voltage becomes n times E. That is true. For 2 it was 1.5 plus 1.5, for 3 it was thrice, for 4 it is 4 times, for 5 it is penta times. So that is how. Upon total resistance is what? All of these resistors are in series because there is no any external wire connecting in between the circuit. So this R plus R plus R plus R, all of these are in series. So external plus all of internal, that is n times R. This is the total current flowing in the circuit. But if I connect them in parallel, for example, this type of configuration, and this circuit is connected across external resistor R. Okay. Now in this case there are m such rows. There are m rows. Okay, m rows. So first of all, okay, let me write the configuration the same. Each cell is configured as EMF E, internal resistance R. Now what do we know about parallel combination? In parallel, terminal voltage across the junction is always equal. That is, in parallel, potential difference is always same. So no matter how many cells you apply in parallel, the resultant potential difference across this hole would be as equal as it is of 1. So this is for current. Total voltage is E because they are all in parallel, but total resistance is, this R is in series with effective resistance of the whole circuit, right? What would be the effective resistance of whole circuit? R divided by M, because there are M number of R resistors which are connected in parallel, so R upon M. So this is in series with this combination, so R plus R upon M. Okay. Now what will be the value of current if I have to apply both series and parallel combination? So let's try it out. Now I am mixing both these circuits. I hope you have noted my point. If you haven't, then kindly pause the video, go back and write the formulas. This time what I am doing is, one cell, second cell, there are n such cells and there are m such rows, and they are all connected across an external resistance R. Okay. Now this is our R, E comma R, each configuration is same, E comma R. Okay. Now what do we know about it right now? There are n such cells and there are how many rows? There are m rows. Okay. I have shown you only 2 lines, there are m such rows. Now I want to find the total current flowing through this resistor. Okay. So what would be the total current? First of all, total current is total voltage. Since they are all in parallel, the voltage in each line would be equal to the voltage across all, because they are in parallel. So voltage across each one loop or one line is what? N times E, and all such NEs are in parallel, so effective voltage becomes same, so NE. Now what is the total resistance now? This R, external resistance, is in series with the whole combination. And what is this whole combination giving me? There are n small r's in a row, so n times R, and there are m such rows, so divided by m. So this is the effective resistance of this whole, and the whole circuit is in series with this resistor. So this is R. So this is the value of total current across such type of combination. This is how we deal with combinations of cells in series and parallel.